Hey everyone, in this video we're going to extend our knowledge of exponentials and maybe even talk a little bit about logs. And I want to start with, will you please solve this problem? 3 to the x plus 3 to the negative x equals 12. I think that says 12 there. Well, we'll find out in a minute. It's either 12 or 2 or 1. Okay. So take a minute to solve this equation. Pause the video, give it a try. Okay, so the first thing I think about here is that I've got 3 to the x plus 1 over 3 to the x equals 12. And like we said in pre-cal, whenever we have an equation with a fraction in it, the first thing I want to do is multiply everywhere by that least common denominator so that I can cancel things out. Now remember, when the bases are the same and we're multiplying, we add the exponents. So 3 to the 2x plus, these are going to cancel, and I'm going to be left with 1 equals 12 times 3 to the x. Okay, now I'm going to put this, maybe it's 2. I'm going to put this in standard form, which means I want decreasing powers. So 3 to the 2x minus 2 times 3 to the x plus 1 equals 0. Now, this factors, I believe. 3 to the x minus 1, 3 to the x minus 1. And, right, because that's going to be minus 3 to the x, minus 3 to the x, so that's minus 2, 3 to the x's. And we've got negative 1 times negative 1 is positive 1. And 3 to the x times 3 to the x, I would add those exponents. 1x plus 1x is 2x. So this is what I've got. Now I'm going to set each of these factors, but they're the same, equal to 0. So 3 to the x minus 1 equals 0. 3 to the x equals 1. Let's take the ln of both sides and bring this down. And so now I get x ln 3 equals ln 1. Well, that's disturbing because now I'm going to divide by ln of 3, but you know that ln of 1 is 0. So this is 0 divided by a number, or 0. So my solution appears to be 0 here. And does that make sense? Well, 3 to the 0 is 1, plus 3 to the 0 is 1, and so 1 plus 1 is 2. Well, that worked out perfectly. Let's think about solving this one, though, also on our calculator. So if I type in y1, if I type in y1, 3 to the x power plus 3 to the negative x power, and then I graph the line y equals 2, I'm going to turn my stat plot off because we don't need that right now, and zoom standard. Did I graph the line too? There it is. Look, we only intersected that place. Now, originally, I thought this might be 12 from my poorly written notes. So let's just take a look at that for a minute. So we would have 3 to the x plus 1 over 3 to the x equals 12. And I suggested that what I would want to do here is to multiply everywhere by that common denominator. And so I've got 3 to the 2x minus 12, 3 to the x plus 1. Okay? So, does this factor? Well, the factors of 1 times 1, 1 times 1 is 1. I can't get factors of 1 that add up to 12. That's how I knew it couldn't be a 12 here, because there was no way this was going anywhere. What about quadratic formula? Well, sure, let's try. 3 to the x equals negative b plus and minus square root b squared minus 4ac all over 2a. So that's 140. 12 plus 140 over 2, 12 minus 140 over 2 equals 3 to the x. So we're not done yet when we find all of this. Let's take it a little further. So I'm saying 3 to the x equals 6 plus square root of 140 is 14 times 10. I can pull out a 2, root 35. So that 2 will cancel with that 2, so I get root 35. And the other answer, 3 to the x equals 6 minus root 35. Okay, so now what would I need to do in order to solve? Well, I would have to take the ln of both sides. And I could bring this power down. So I get x ln of 3 equals the ln of 6 plus root 35. So when I divide both sides by ln of 3, I get x equals ln of 6 plus root 35 all over ln of 3. And then here, I'm going to have something similar, except it's going to be x equals ln of 6 minus root 35 all over ln of 3. So let's check out those answers. We know, second quit, that ln of 6 plus square root of 35 divided by ln of 3 is going to be 2.255471522. Okay? And if we go back and we change that to ln of 6 minus square root of 35 and divide that by ln of 3, we end up with negative 2.255471522. Oh, isn't that interesting? And so let's check this out graphically as well. So graphically, I'm changing this 2 to a 12. And I'm going to need to change my viewing window to get more y into it. So let's go to 20 in steps of 2. Second, calculate intersect. I bring my cursor close to the point of intersection. I hit enter, enter, enter. And so I end up with 2.2554. There it is. So I can do these problems on my calculator. I can do these problems algebraically. But did you catch the algebra that I had to do? I mean, were you really paying attention to it? Especially since you'll probably have to take a test on it. We saw this as this. And because I have a fraction, I multiplied everywhere by that least common denominator. So I've got 3 to the 2x. These cancel. Plus 1 equals 12 times 3 to the x. This is not 36 to the x. This is 12 of these 3 to the x's. Okay, and so then because I saw a quadratic, I moved this over. Plus 1 equals 0. And then I would try and factor. Now, in this problem, we can't factor, so I actually need to graph on my calculator to find this. I guess I showed you also I could use quadratic formula, but remember when we use quadratic formula, instead of the normal x equals negative b over 2a stuff, this is 3 to the x equals negative b over 2a. And then we still needed to solve for x by taking the ln of both sides. Okay, wow, I thought I was comfortable with algebra. And then I saw a problem like that. Okay, don't forget to be asking questions from the homeworks, either in GroupMe or in our live sessions. Let's take a look now at this table. of f and g values. So here we've got a table. It's got x, f, and g values. 0, 1, 2, 3, 1, -2, 0, 4, pi, 3, e, 1. All right, now what I want you to do is to use this table to evaluate some expressions. I will say that a table problem is almost a guarantee on every AP free response set of problems. So I would expect to see a table, and therefore you're going to be engaging with tables quite a bit this year. Okay, so the first one I want you to find is g of f of 2. Okay, now, we talked about two ways of doing composition. One, where I take f of x and plug it into all the x's of g of x, simplify, and then plug in a 2. But I can't do that here because I don't have an f of x function and I don't have a g of x algebraic function to plug one into the other of. Instead, I have to find f of 2. F of 2 is 0, so I can replace f of 2 with 0. And then g of 0 is pi. Okay? See how that works? So will you please be so kind as to do B on your own? G of f of 0. Please find g of f of 0. Pause the video, give it a try, come back when you're done. Okay, that was fast. Good job. F of 0 is 1. So now I want g of 1. G of 1 is 3. So I know g of f of 0 is 3. Okay, let's just do one more of those. How about f of g of 3? Give this one a try now. Excellent. So let's go. G of 3. G of 3 is 1. So we need f of 1. And f of 1 is -2. So f of g of 3 is -2. This is evaluating composition of functions with a table. And you can pretty much expect to see a table. Great. Now, let's talk about graphs. I remember that we had in our reference graph conversation y equals b to the x. And remember those reference points were -1, 1 over b, 0, 1, and 1b. And that b is our exponential base. So let's think about then what would y equal 2 to the x be? That would be -1, 1 over 2, 0, 1, and 1, 2. Or if I had y equals 3/2 to the x, I would have -1, 1 over 3/2, which is 2/3, 0, 1, and 1, 3/2. Yeah? Okay, so with this reference graph in mind, let's take a look at applying our transformations to some exponential functions. So let's go with y equals 2 times 3 to the x plus 1 minus 4. Okay? So when I look at something like this, I only see 3 transformations. 1 on the inside of the function affecting the x's, and 2 on the outside affecting the y's. Remember, we do the y transformations in PEMDAS order, and if we had more than one x transformation, we would use SADMEP order. Don't forget you're applying these to the reference points. Our reference points are -1, 1 over 3, 0, 1, 1, 3, and don't forget, with exponentials, y equals 0 is our reference graph horizontal asymptote. And because this is a y value here, any y transformations get applied here as well as here, here, and here. So I'm going to subtract 1 from the x's. What am I going to do to the y's? Am I going to subtract 4 or multiply by 2? Well, PEMDAS says I'm supposed to do the multiplying by 2 before I do the subtracting 4. And by the way, this is a minus 4 under the glare spot that you can't see the minus 4. Okay, so I'm going to multiply all the y's by 2, including this y. So I get negative 2, 2/3, negative 1, 2, and 0, 6. 0 times 2 is still y equals 0 for the horizontal asymptote. Next, I'm going to subtract 4 from all the y values, including this one. So I see my new horizontal asymptote is at negative 4. This shifts the whole graph down 4 places. So instead of a horizontal asymptote at 0, I've got a horizontal asymptote at negative 4. Okay, minus 12/3 plus 2/3 is going to be minus 10/3. Negative 1, negative 2, and 0, 2. So these are the points. This is the horizontal asymptote. And let's carve out some space on this board so that we can graph. Remember, I need you to label your points on the graph. Here's y equals negative 4. We know at 0, we have a y value of 2, 0, 2. So my graph is this, it's exponential growth. I pass through negative 1, negative 2, and over here, negative 2, negative 10/3. Now, this is negative 4, that's negative 12/3, so I know I'm a little bit above it, and that's great. Any questions about graphing this exponential? Well, if you have them, write them down, or better yet, send them out on the GroupMe right now. Okay, in the meantime, why don't you graph y equals 1/2 times 4 to the 3x plus 5, and this will be plus 7/2. Okay, y equals 1/2 times 4 to the 3x plus 5 plus 7/2. Why don't you pause the video and graph this, come back if you have questions, or when you're done and want to check your answer. Okay, I'm starting here with the reference points, which are negative 1, 1 over b, our base is 4, so 1/4, 0, 1, and 1, 4. Don't forget the horizontal asymptote, y equals 0. Many students leave this off, and because they leave it off, they draw a horizontal asymptote at 0, even though the horizontal asymptote isn't at 0, but at 7/2. So please make sure you include this every time. So now I see 2 y transformations and 2 x transformations. I do the x transformations in SADMAP order, which means I'm going to be subtracting 5 from all the x's first, and then I see I do PEMDAS order with the y transformations, which means I'm multiplying the y's by 1/2. This is also a y, so I'm also multiplying here by 1/2. So I have negative 6, 1/8, I have negative 5, 1/2, and I have negative 4, 2. And this, of course, still stays y equals 0, the horizontal asymptote. Okay, those are our transition points. Now we have to go back and finish our transformations. I see multiplying the x's by 3, but I know inside is opposite land, so I have to divide the x's by 3. This is not an x value, so I'm not going to divide by 3 here. I also see this y transformation. I'm supposed to add 7/2 to all the y's. And here's another y value, so I add 7/2 here as well. So what do we have? We have negative 2. This is 28/8 plus 1/8 is 29/8. We've got negative 5/3. 1/2 plus 7/2 is 8/2 or 4. And then we've got negative 4/3 4 halves plus 7 halves is 11 halves. Okay, so that's 5.5. There's 4. And what about this one? This one was 29 over 8. Well, 8 goes into 29 3 times for 24 with 5/8 left over. So this is the smallest y value, this is the largest y value, and this makes sense to me because I'm expecting exponential growth. I want my biggest y value over here and my smallest y value over here. And our horizontal asymptote, y equals 3.5. And this is between 3.5 and 4. So that's great that I'm a little above my horizontal asymptote. Let's take a look at the graph of this. Here we have our horizontal asymptote, y equals 7 halves. And I've got swoosh, my exponential growth curve. This point over here, negative 2, 29/8. This point here, negative 5/3, 4. And this point over here, negative 4/3, 11 halves. And there's our graph. Any questions about that? Okay. Send them out on the GroupMe. Bring them up at our next live Zoom. Why don't we try one more? Or better yet, why don't you try one more? How about negative 4, 3 to the 2x minus, I want to use a number I haven't used, so I'm going to use 1. And then I'm going to say plus 6. Okay? Please graph. Oh, did I really say 3? No, I'm sorry. I meant 1/5. Okay. So please graph this one. Come back when you're done so we can check answers together. Hi. I'm going to start off by writing down the reference points. Negative 1, 1 over b. Well, 1 over 1/5 is the same as 1 times 5 over 1, or 5. Then I have 0, 1, and 1, 1/5. Notice my biggest y is over here and my smallest y is over here, which means I have exponential decay. Why is this decay? Well, it's decay because, 1/5, that's the same as 5 to the negative 1 raised to the 2x minus 1, and when I raise a power to a power, I multiply. So I got this, and because of that negative power there, I know I have exponential decay. We also talked about when the rate was between 0 and 1, you would have exponential decay. And that's great so far, except I haven't begun to apply my transformations. Here, inside the function, I see that I'm supposed to add 1 to all the x's. Plus 1, plus 1, plus 1. And come on, Kukla, don't be lazy. Write out that horizontal asymptote at y equals 0. And then we come back and do this this y transformation. This is multiplication. It's not subtraction. This is multiplying by negative 4. So what do I need to do? Multiply by negative 4 to all the y's. So my transition points will be 0, negative 20, 1, negative 4, 2, negative 4/5. And 0 times negative 4 is still y equals 0. Okay, that's halfway through. Let's take care of the next round of transformations. I need to divide the x's by 2. And I need to add 6 to all the y's. Plus 6, plus 6, plus 6, plus 6. So I see my horizontal asymptote is now at y equals 6. But let's take a look at these other values. 0, negative 14, 1/2, 2, and 1. This is 30/5 minus 4/5 is 26/5. That's 5 and a little bit. Okay, so this is a very big number. This is more than 5, which is more than 2, which is more than negative 14. I thought we said that this was an exponential decay function. Well, we reflected our exponential decay function. So instead of being this, we've got something like this. And that makes sense to me because this number goes over here, and this one here, and the biggest y value goes over here. So let's graph this. Okay, we know our horizontal asymptote is at y equals 6. But this time I've got 0, 0, negative 14. I've got 1 half, 2, and I have 1, comma, 26 fifths. Now, if I draw in my curve will look like, whoa, look like that. Because I have that regular exponential decay, but this negative flips the y values, and so this is my shape now. Okay? Excellent. Guess what? I'd be expecting to have to graph something like that on a CFA or on a test. So please make sure you're comfortable with these things. Okay, what's next? Well, next I want to talk about inverses for a second, okay? What do we remember about inverses? A function has its inverse. How can I tell if a function has an inverse? A function has an inverse if this isn't how do I make the inverse of a function. We'll do that in a few minutes. Right now, I just want to know a function has an inverse if what's true. How can I know if a function has an inverse? Why don't you take a minute to see if you can remember anything from pre-cal algebra 2. I don't think you talked about inverses in algebra 1. You might have, depending on your teacher. So what do you know about inverses? Well, the first thing I'd say is if a function is 1 to 1, then the function has an inverse. The problem with this definition is that most people have forgotten what it means if a function is 1 to 1. Well, what it means is each input goes to one output, and each output goes to only one input. Okay? This is what I know if a function is 1 to 1. So the first part is each input goes to one output. So if I have the input of 2, I'm only going to get one y value there. I'm not going to get two different y values there. And you know what would mean if I had two y values there? It would mean that I wasn't a function. So this one guarantees that my original function isn't, my original relation is a function. And then here where we talk about each output only going to one input, that's what claims that the inverse is a function too. We're only going to care if our inverse is also a function. So what does this mean? How am I supposed to deal with this information? Well, we took this information and we figured out a couple of ways to figure out if a function has an inverse. And the most common way to figure this out is, or if a function is 1 to 1, does it pass, does the graph of the function pass the horizontal, not vertical, horizontal line test? So if I have a graph and I have a function, if that horizontal line can be driven so it crosses in more than one location, we say no inverse here. No inverse. we failed the horizontal line test. Now, notice the horizontal line test means I had this y value at this x, but I had the same y value somewhere else. Each output, each y value goes to only one input. This line here goes to two different inputs. It goes to this input here, and it goes to this input here. And therefore, we aren't one-to-one. We don't have an inverse. Now, when we ran into this last year in pre-cal, we said, well, we like parabolas. We don't want to get rid of all of them. And so do you remember what we did? We said, okay, y equals x squared, but for x greater than or equal to 0. Now if I graph this, look what happens. 1, 1, 2, 4, 0, 0. I'm considering the parabola, but only for x is greater than 0. Does this function pass the horizontal line test? Sure does. So if we fail the horizontal line test, we can always look to see if we can restrict the domain in order to get a situation where we would pass the horizontal line test. So this y equals x squared does not have an inverse. This y equals x squared, but for x is only greater than or equal to 0, like this picture, this one does have an inverse. Okay? What else can we say about knowing if a function has an inverse? Well, if I think about a table, so let's take a look at these three cases and see if we can determine which of these has an inverse. Okay? Now, you can always graph these. So if I draw in 1, 2, 2, 2, 3, 2, 4, 2. Is this function going to pass the horizontal line test? No. So while it is a function, it does pass the vertical line test. This function has no inverse because of the repetition in the range. Repetition in the range is another way I can tell that a function won't have an inverse. What about this situation? It's similar but different. It's got one x value and a bunch of different y values. Well, the problem here is not having an inverse, because I don't see any repetition here, but I have repetition in the domain. And what that means is I have a vertical line. And what that means is this thing is not a function. And if it's not a function, I really don't care if it has an inverse or not, because all my inverses are inverses of functions. This is not a function, so I'm not going to be having an inverse for something like this. So if you see repetition in the domain, we say that's not a function. If we see repetition in the range, then we say that function has no inverse. Do you see any repetition in the domain or range here? So we say this function has an inverse. So we've talked about a couple of ways of determining whether a function has an inverse or not, right? We said, okay, we want each input to go to only one output. We want each output to go to only one input. For a lot of people, that's confusing. So then we say, okay, let's use the horizontal line test because you're pretty good at graphing. And so you can see, oh, look, it crosses the horizontal line. The horizontal line crosses the curve in two places. That means no inverse possible, like this situation. Okay, and then we looked at tables and said if we see repetition in the range, that's not going to have an inverse. Repetition in the domain, that's not even a function. And so we're looking for no repetition in the domain or range. You know, we can talk about the rule of 4 here. We've looked at graphically, we've looked at numerically through a table. Let's also consider algebraically. But my problem with considering algebraically is the first thing I do is I picture this in my head. Oh, 2x plus 1. There's 2x plus 1. Does this line pass the horizontal line test? Yes. So this has an inverse. What about this function? Negative 2, 1, 4. Does this function have an inverse? No, because it fails the horizontal line test. So even though I could tell you y equals x plus 2, x minus 1, and x minus 4, I know what that is. That's a polynomial. I could even FOIL it out if I really had nothing better to do. But this is hard for me to determine whether or not this third-degree polynomial will pass the horizontal line test. Some third-degree polynomials pass the horizontal line test, just not all of them. So I really end up thinking about things like this graphically. One of the reasons we practiced as much graphing as we did in pre-cal was so that you'd have developed, by the time you got to calculus, a graphical sense. You could look at algebra and think about it graphically, just like Descartes wanted us to do. Okay, so let's move on. We've talked about how do I know if a function is one-to-one, or how do I know if a function has an inverse. Hey, but we haven't talked about how do I make an inverse. Okay, how do I make an inverse? If f of x equals 2x plus 1, this was the function we just had, and I said, yeah, that's a linear equation. That's going to pass the horizontal line test. Well, now that I know it can have an inverse, how do I make the inverse? How do I make f inverse of x appear? Do you remember what we did last year or the year before? To make an inverse, we want to switch x's and y's, then solve for y equals. Okay, so let's take a look. I've got y, I've got x. I'm going to switch them. So we're going to have x equals 2y plus 1. But then I have to solve for y. I'm not done yet. I have to get y equals by itself. So I'm going to subtract 1 from both sides, and I'm going to divide by 2 everywhere. So I get 1/2 x minus 1/2 equals y, and that's what my inverse function will be. Okay? All right, so switch the x's and y's and solve for y is one way to make an inverse. It's the way I would make an inverse by using algebra, okay? So what about this? Y equals x squared minus 5x plus 6. Well, my problem with this is I can switch the x's and y's, but how do I solve for y? This is a problem, isn't it? I can't get y by itself. I can factor this. This is y minus 2, y minus 3 equals x. But I can't get... And look, if you said, hey, let's subtract 6 from both sides, you text me your address and I'll come over with my pool noodle and pop you on the head. Okay? No, this is bad. Don't do that. So sometimes I can't algebraically solve for the inverse, and that's a little frustrating at times. All right, so one way is algebraically to make the inverse. What about graphically? So our function, f of x, passes through these points. But what about our function, f inverse of x? I mean, I know this has an inverse because I don't see any repetition in the domain or range. So what points must exist on f inverse? If these are the points on f of x, what points must be on f inverse of x? Well, remember, when we were thinking about this algebraically, we switched the x's and y's. So 5, 7, negative 1, 2, 1, 2, 3, 4. There's my inverse function. Okay? Now, what about from a graph? So we switch the x's and y's when we're talking about algebra. We switch the x's and y's when we're looking at a table. How about a graph? Let's go back to 2x, y equals 2x plus 1. Here's our function with negative 1/2 and 1. This is f of x. And now I want to graph f inverse of x. So how do I do that? Well, I got to switch the x and y's. Remember, these are ordered pairs. So when I switch the x's and y's, I get 0, negative 1/2, which is down here, and I get 1, 0, which is over here. 1, 0. Okay, so I'm going up 1/2 and over 1. I know that these lines will, somewhere out there in space, intersect because they don't have the same slope. This goes up 1/2 and over 1, 1/2 over 1, which is a slope of 1/2, whereas this one has a slope of 2. So this one's much steeper than I made it look on the graph. This one should have a shallower slope. In fact, let's pull out our calculator and graph that for a second. Okay, I want to graph y equals 2x plus 1, and I want to graph, was it 1/2 x minus 1/2? So 1/2 x minus 1/2, and zoom standard window. There we go. Now, something else. We talked about how do I make an inverse from a graph, from a table, and from some algebra. But what if I'm already given two functions? How can I tell if two functions are inverses of each other? And that's the third topic I want to bring up, or the third question regarding inverses. How do I know if two functions are inverses? Well, it depends on what we're given. If I'm given a t-chart, x and f of x, x and g of x, 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 0, 8, 1, 2, 3, 4. Well, are these inverses of each other? Did I flip the x's and y's to get these? No. This should be 7. If this were 7, then all the ordered pairs would have x's and y's switched, and these would be inverses. So from a table, I'm looking to see if the ordered pairs have been flipped. What about from a graph? How can I tell by looking at a graph if two functions are inverses? These two functions are inverses, but what is it about inverse functions? Well, I know two things, okay? The first thing I know is there's negative 1/2, there's negative 1/2, there's 1, and there's 1, okay? And so this was our f, and this was our f inverse. So there's a couple things I notice when I look at a graph, and this is another reason why I want you to label the points on the graph so that you can see these things. Okay, so this is 0, negative 1/2, and this is 1, 0. Okay, the first thing I want to notice when looking at a graph of two functions to determine if they are inverses or not, the first thing I want to look at is, are the ordered pairs flipped? Are the x's and y's in the ordered pairs flipped? If they are, then yes, these functions are inverses of each other. There's something else I know graphically. Graphically, inverses reflect across y equals x, the line y equals x. So if I have two functions that are inverses and I draw the line y equals x, I should see them splitting right in half. See, look at that. So they reflect across the line y equals x. And the xy ordered pairs are switched. That's what I would see as well. Okay, so we talked about from a table, if the x's and y's here are the y's and x's over here, if we've switched, we can see that here as well. 0, 1 becomes 1, 0, negative 1 half 0 becomes 0, negative 1 half. Then that's how we can determine if two functions are inverses. However, algebraically, the bar is a little higher, okay? We have to do something special in order to determine if two functions are inverses of each other. So, for example, f of x equals x to the third, and g of x equals cube root of x. How can I determine if those are inverses of each other? Well, I don't have a table, I don't have a graph. I guess I could graph these things and see if they have an inverse. But ideally, I'd like to come up with a purely algebraic approach for this. And here's what we do. It's composition. Use composition to determine if two functions are inverses. And what does that mean? Well, it means that I want to find f of g of x, but I also need to find g of f of x, and furthermore, that this composition and this composition should equal x. When I do the composition, I should get y equals x. Hey, there's y equals x now. All right, so let's try the composition. Let's take g of x and plug it into all the x's of f of x. I'm going to take this and plug it in there. So I've got cube root of x raised to the third, which is the same as cube root of x raised to the third, which is x. Well, that's great, but that's not sufficient. That's just f of g of x. I still need to do g of f of x, which means I need to take this and plug it in there. Cube root of x to the third. Well, that's x to the third raised to 1/3, which is again x to the 1, or x. I have to do both compositions. I can't just do one. And when I do both compositions, they must equal x. This is called, and you'll see this word a lot, verify. The language in the homework problems or the test problem would be verify that these two functions are inverses of each other. Okay? All right, so let's take a look at this. You're going to love this. F of x equals 3x plus 1 over 2x minus 5, and g of x equals 5x plus 1 over 2x minus 3. Are f and g inverses of each other? Duh. It would be really hard to determine if these were inverses of each other by looking at the graphs of them. I definitely don't recommend graphing these on your calculator and trying to figure it out. You might want to try by hand, but it'll be really time-consuming and still unsatisfying. Instead, we need to do f of g of x, and we need to do g of f of x. Now, what does that mean? That means I'm supposed to plug g of x into all the x's of f of x. I'm supposed to take this thing and put it in here and put it in here. All right, so what does that look like? 3 times 5x plus 1 over 2x minus 3 plus 1 over 2 times 5x plus 1 over 2x minus 3 minus 5. Okay, so now what? Well, I can approach this algebra in one of two ways. Either I can distribute, make a common denominator, combine like terms, distribute, make a common denominator, combine like terms, and then flip and multiply and solve and see if I get x. Now, if these really are inverses, then we know when we do the composition we should get x. There's another easier algebraic way to approach this, and that's about taking this fraction and multiplying by this common denominator. I have it on top and bottom, 2x minus 3. Do I have it? Yes, this is the same common denominator. I'm going to multiply by 2x minus 3 on top and bottom. And why is that? Well, this gets distributed here, and it gets distributed here, but when it gets distributed over here, this cancels that one out. So on top, I'm going to have 15x plus 3, and don't forget it was 1 times this, so plus 2x minus 3. On the bottom, when I multiply by 2x minus 3 and distribute, these will cancel out again, and so I'll have 2 times 5, or 10x plus 2 minus this 5 has to get distributed here, 10x plus 15. Okay, well, let's tidy this up and see what happens. So I got 17x over here, and I get 17 on the bottom. The 17's cancel, and I get x. Son of a gun. These are inverses of each other. Well, I don't know that yet. I did f of g of x, but now we need to do g of f of x. Before I ask you to do that, I'm actually going to show the other way to do this problem that I mentioned originally. 3, 5x plus 1 over 3, 5x plus 1, 2x minus 3 plus 1 over 2, 5x plus 1, 2x minus 3 minus 5. So even though I prefer doing it that first way, I notice that most students do this. They do the distributing, 15x plus 3 over 2x minus 3 plus 1, and then they say, oh, I need a common denominator, so they do the 2x minus 3 over 2x minus 3. And then on the bottom, they distribute and get 10x plus 2 over 2x minus 3. And then they need to make that common denominator again, like this. Okay, so I've got to do some distributing here, and then I can do some combining like terms. So let's do some combining like terms and some distributing. So now I'm going to go over here and get 15x plus 3 plus 2x minus 3 over 2x minus 3 over 10x plus 2 minus 10x plus 15, all over 2x minus 3. Now there are like terms to combine on top and bottom. Where does that get me? That gets me 17x here over 2x minus 3. That gets me 17 here over 2x minus 3. And now I have to do that flip and multiply. 17x over 2x minus 3 times 2x minus 3 over 17. And I see these cancel and these cancel, leaving me with x. Okay, so you've got two different ways of simplifying the composition of these functions. And my recommendation, since these are going to have the same denominator, that you do that first approach. But if you're not comfortable with the first approach, by all means take this longer path. When you do g of f of x, okay? And, if this shows up on a test and you haven't practiced it, yeah, that's on you. So please give this a try. Pause the video, give this a try, and come back when you're done, and we can look at what my answer looks like. Okay, welcome back. So I'm going to take f of x and plug it into each of these x's of g of x. So I've got 5 times 3x plus 1 over 2x minus 5 plus 1 over 2x, and I replace x with all this, 3x plus 1, 2x minus 5, and then minus 3. Okay, so we did the composition, and this is where I was saying, hey, I notice these both have the same denominator, so why don't I multiply on top and bottom by 2x minus 5. I'm going to multiply by 2x minus 5 on top and bottom. Okay? I need to distribute that to each of these. And so my top will look like 5 times 3x plus 1 plus 1 times 2x minus 5. And this cancels that out. This will also cancel this out, so I'm only going to have 3x plus 1 on the bottom, minus 3. This didn't cancel out here, so I've still got 2x minus 5. Okay, so I need to distribute and combine my terms. 15x plus 5. Here I have 2x minus 5. And on the bottom, I've got 6x plus 2 minus 3, 6x minus a minus is plus 15. Okay, and is there any tidying up I can do? Well, those cancel, and those cancel, and I have 17x over 17 or x. Okay, so I can determine if two functions are inverses by composing them, and I have to verify this fact that they're inverses by doing f of g of x and g of f of x, and showing in each case that I get x. All right? Okay. Next, I would like you to make inverses of each of these functions. Okay, so if f of x equals 3x plus 1, what's f inverse of x? So give this one a try and tell me how to find the inverse. Right. When we talked about finding inverses before, we said we would switch the x's and y's and solve for y. And you can write x minus 1 over 3, or you can understand this as 1/3 x minus 1/3. So I can split this into two fractions. Okay, so that's my f inverse in that situation. What about something a little more challenging, like y equals 2 cube root x minus 1 plus 3? How would I find the inverse here? What would the inverse be here? Why don't you please find the inverse for f of x? All right, so we're going to switch the x's and y's again. And then what do we do? Well, we want to solve for y. So I'm going to have to subtract 3. Remember, we're doing SADMAP here because we're solving. When we're solving, we're doing SADMAP, so I have to undo this, and then undo the exponent. Why is that an exponent? Because it's y minus 1 to the 1/3 power. That's an exponent. I need to undo it. And then what's in parentheses? Because remember, we have y minus 1 inside that exponent, so those are parentheses. So I've got 4 steps to do here. I get x minus 3 equals 2 cube root of y minus 1. I divide everywhere by 2. X minus 3 over 2 equals cube root of y minus 1. Now I have to cube both sides. And so I get y minus 1 equals x minus 3 over 2 cubed, and finally add 1. So I'll end up with y equals x minus 3 to the third. I know 2 to the third is 8, and then plus 1. So this cubic function is the inverse of this cube root function. This is f inverse. Okay? What about this last one? What can we say here? Y equals 2 to the x. Okay, I want to know the inverse of this. Switch the x's and y's. Now what? Okay, so maybe you remember from solving exponential problems, because here's an exponential problem, I could take the ln of both sides. Okay. In fact, I want to come at this two different ways. I want to say x equals 2 to the y. And I also want to consider log base 2. Okay. So here, I can use that power rule, and I get ln of x equals y times ln of 2. And then I would divide by ln of 2 on both sides. And so I get y equals ln of x over ln of 2. This is not equal to the ln of x over 2. No, don't do it. These are two different ln's. No, don't do it. However, there is something called the change of base formula. And I'll talk about that in a minute. So right now, I see this as my inverse. Okay? What about here? Well, we take the log base 2 of both sides. I can bring this down. And so I have log base 2 of x equals y, log base 2 of 2. Hey, what is log base 2 of 2? What was log base b of b? If you remember, it's 1. And so this is also the inverse. And remember that change of base formula I just mentioned? Well, surprise! The change of base formula says when you see this base, you can rewrite this as ln of x over ln of the base. You could actually rewrite it with any log base. It doesn't have to be log base e like these ln's. We could also do log base 3 of x over log base 3 of 2. Probably would never do that. I might use the common log, though, log x over log 2, and that would work as well. But this and this are the same, and to get from one to the other, I use this thing called the change of base formula. What I'm pointing out, though, more importantly, is that the inverse of this exponential function is this log function, okay? And what do we know about logs? Well, since this log is the inverse of this exponential, and this exponential passes through the points negative 1, 1 over b, 0, 1, 1, b, and has a horizontal asymptote at y equals 0, and I know this is the inverse of that, then I know this function passes through the inverse points, switch, 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 and so I get 1 half negative 1, 1, 0, and 2, 1. And because I'm switching x's and y's, what happens to this? Well, horizontal asymptote y equals 0 now becomes x equals 0, which is a vertical asymptote. And so let's take a look at these two graphs. Oops. Let's take a look at these two graphs. First, the exponential has a horizontal asymptote at y equals 0 and passes through the points negative 1, 1 half, 0, 1, and 1, 2. But this inverse function passes through 1 half negative 1, 1 half negative 1, 1, 0, and 2, 1. We also know that this thing has a vertical asymptote, x equals 0. Now, are these inverses of each other? Well, do they reflect across the line y equals x? Yeah, sure looks it, even on my really bad hand-drawn graph, where the scale isn't necessarily consistent. They look pretty much like they're reflecting across that line. Also, I see that the ordered pairs are switched. Okay, so those two things confirm for me visually that this algebraic work we did to find this inverse function was correct. So let's just reiterate. One, we've got a new reference graph. Y equals log base b of x passes through 1 over b negative 1, 1, 0, b, 1, and has has a vertical asymptote of x equals 0. We're going to need this, I promise. So please make sure you know your reference graphs. You'll also need the exponential one. We talked about that. Negative 1, 1 over b, 0, 1, 1b, and a horizontal asymptote at y equals 0. So you should be comfortable with both of these. What else did we talk about today? Well, we talked about composition, and the reason we brought up composition today was because one of the things we said about inverses was that in order to verify that two functions are inverses, we need to do f of g of x equals g of f of x. Oops, I did that twice. G of f of x equals f of g of x, and that composition, those compositions, you have to do both, equal x, okay? All right, what else did we say? Well, we said three things. How do I know if a function has an inverse? And we talked about one input for every output and one output for every input, but what most students do is they do the horizontal line test. Okay? We also talked about how do I make an inverse of a function. And we said what we would do in this case is we would switch x's and y's. And if we were doing it algebraically, we'd want to solve for y. But if I'm just doing a table, I'm just flipping the inputs and outputs. If I'm on a graph, I'm switching the ordered pair x and y values. The only time I don't switch x's and y's, put a little asterisk here, is word problems. We talked about this in pre-cal last year. In word problems, I don't switch the x's and y's and solve for y. Just solve for y. Okay? All right. And the last thing we looked at inverses was how do you know if two functions are inverses? And what we said here was we would look, for example, at a table and see if the inputs here were the outputs over here and the outputs here were the inputs over here. Or from a graph, we would say, hey, are the ordered pairs switched? Because we know an ordered pair on the original function. Is it switched on the inverse function? That's going to be really important. That question comes up every year on the AP exam when we have to do calculus with inverse functions. So really remember, when we're doing inverse functions, we're switching the x's and y's. We should see that on a graph. We should see that from a table. And if we're talking about if I know two functions are inverses, this is where we have to algebraically do the composition. We'd want to see algebraically f of g of x equals g of f of x equals x. All right. Well, I think you're ready to go off and try assignment 13, which I see here is bookwork. Remember, these pages will be scanned and in our Chapter 1 folder for you to use. Students will actively read. Remember, you should be reading these pages, reviewing your notes, certainly watching the video before you do these problems. And then, please do these problems. Okie doke? Oh, and there's a note here. For numbers 26, 28, 29, and 42, the directions in the book say do them parametrically. Yeah. Don't do them parametrically. That's crazy. We don't need to worry about that. Just use our transformational graphing, and please give exact value graphs instead. All right. I hope this was helpful. I look forward to taking any questions you have.